Hey guys, I'm Sir Brains and Gains, and today we're learning k-nearest neighbors, or KNN, a simple machine learning method that predicts outcomes by looking at nearby examples. KNN is a supervised, non-parametric, instance-based learning algorithm. It stores labeled examples and predicts a new observation based on which training points are most similar to it. KNN is called lazy learning because it does very little model fitting up front. Most of the real work, including distance calculations and neighbor searches, happens when a prediction is requested. For classification, KNN finds the nearest labeled examples around an unknown point. Those neighbors vote, and the class with the most votes becomes the prediction. KNN also handles regression. Instead of voting on categories, it finds nearby observations with numerical targets and typically averages those values to predict a new continuous value. A prediction begins by comparing the new point with the stored training observations. The algorithm calculates a distance from the new point to each example in the dataset. Next, we choose k, the number of neighbors to use. If k equals 5, KNN sorts the distances and keeps only the 5 closest observations. For classification, those 5 neighbors vote. In this example, 3 neighbors are blue and 2 are red, so the majority decision predicts the new point is blue. For regression, nearby target values are averaged. If the 4 nearest values are 10, 12, 14, and 16, their average is 13, so 13 becomes the prediction. But everything depends on how we define closeness. Euclidean distance measures straight-line distance, while Manhattan distance measures grid-like movement. Next, we'll examine how these distance metrics affect KNN. Euclidean distance measures the direct straight-line distance between 2 points. It's one of the most common distance measures used with KNN, especially when numerical features are properly scaled. Manhattan distance measures how far apart 2 points are by adding the absolute differences across each feature. Think of moving through city blocks instead of traveling in one straight line. KNN is not limited to Euclidean or Manhattan distance. Minkowski generalizes both. Cosine distance can compare vector direction, and Hamming distance is useful for binary or categorical style data. Feature scaling is extremely important in KNN. If one feature ranges into the thousands, while another ranges from 0 to 1, the larger scale feature can dominate the entire distance calculation. The value of k controls how local the prediction is. A very small k can overreact to noise, while a very large k can smooth away useful patterns. Validation helps find a better balance. As we add more features, distance becomes less informative because observations tend to spread apart. This problem is part of the curse of dimensionality and can seriously reduce KNN performance. Classification can produce a tie when multiple classes receive the same number of votes. Common solutions include choosing an odd k, using distance-weighted voting, or applying a consistent tie-breaking rule. Standard KNN gives every selected neighbor equal influence. Weighted KNN gives closer observations more influence, which can improve predictions when nearby points are more informative than farther neighbors. KNN is simple, intuitive, and works for both classification and regression. However, prediction can become slow on large datasets, and performance depends heavily on scaling, feature selection, distance, and k. So far, we've learned how KNN finds nearby examples, measures distance, chooses neighbors, and makes predictions. Next, we'll put everything together and walk through complete KNN examples step by step. Now let's put everything together with a complete classification example. We have 2 classes, a new green point, and we'll use k equals 3 with Euclidean distance to make the prediction. First, we calculate the Euclidean distance from the new point to every labeled observation. This gives us a numerical way to measure which existing points are closest to the new one. Next, we sort all observations from nearest to farthest. Because k equals 3, we only care about the 3 smallest distances at the top of the list. The 3 nearest neighbors are A3, A5, and A2. All 3 belong to class A, so these are the observations that will determine the final classification. Now the neighbors vote. Class A receives 3 votes, and Class B receives 0. Since Class A has the majority, the new point is classified as Class A. Now let's switch from classification to regression. Here the target is numerical. We'll use k equals 4 and predict the green point using the values of its 4 nearest neighbors. The 4 nearest target values are 10, 20, 30, and 40. Their average is 25, so 25 becomes the predicted numerical value for the green point. KNN can create flexible decision boundaries because predictions depend on local neighborhoods. Unlike a simple linear classifier, the boundary can bend around different clusters and patterns in the data. KNN works well for smaller or medium-sized datasets, nonlinear patterns, and problems where simplicity matters. Be more careful with large, high-dimensional, noisy, or poorly scaled datasets. The main idea is simple. KNN predicts from nearby examples. Distance defines closeness. K controls the neighborhood. Classification uses voting, and regression uses averaging. Proper scaling and thoughtful parameter choices are essential. Before wrapping up, remember that KNN can perform poorly when it is set up incorrectly. Common mistakes include skipping feature scaling, choosing K without validation, keeping irrelevant features, and ignoring dataset size or class imbalance. A stronger KNN workflow starts by scaling features, separating training and test data, and tuning K with validation. You should also compare distance metrics and consider weighted neighbors when closer observations deserve more influence. The complete workflow is straightforward. Collect labeled data, clean and scale the features, choose K and a distance metric, calculate neighbors, make the prediction through voting or averaging, and finally evaluate performance on unseen data. Nearest neighbor ideas can also support recommendation systems. Users or products can be represented by features, then compared for similarity. Items liked by similar users can become potential recommendations for someone with related preferences. KNN can also serve as a simple baseline for pattern recognition. A new image or handwritten character can be compared with labeled examples, and nearby examples help determine its class when the features represent similarity effectively. Compared with other models, KNN requires little traditional training and can handle nonlinear patterns naturally. However, predictions can be slower than linear models because distances must be calculated against stored examples. Implementing KNN in Python follows the same concepts we learned today. Load the data, split training and test sets, scale the features, configure the KNN model, make predictions, and evaluate the results. At a glance, remember 4 things. Classification uses a neighbor vote. Regression usually averages nearby values. Distance determines which observations count as close, and tuning K and feature scaling can dramatically affect performance. You now understand the core ideas behind K-nearest neighbors, what the algorithm is, how it handles classification and regression, why distance and scaling matter, how K changes predictions, and when the method is useful. Thanks for watching. I hope you enjoyed today's lesson and now have a solid understanding of K-nearest neighbors. If this helped you learn something new, don't forget to like, share, and subscribe to Brains and Gains. I'll see you in the next lesson.